Right, guys. So now when you all are experts in multivariate analysis, we will move on and spend some more time working with the notebooks, but doing some univariate data analysis. I will just spend a few minutes in the beginning to kind of show or present some of the methods I intended for you to use during the tutorial. So we can start from there. So of course, multivariate statistics is quite often a very intuitive way to start using to analyze metabolomics data. And this is, of course, because you have a lot of variables. It's most common type to address statistical issues when you have more variables than observations. But you can still analyze data like that using univariate statistics. Sometimes you may be interested in specific metabolites, whether it differs between two different conditions in your data sets, two different groups. Of course, there are specific issues that comes with the fact that we have, contrary to what is usually the case with univariate statistics, we have more variables than observations. In this case, this will present some issues which we have to deal with, and we can deal with. And Epit talked about this a bit already in the first lecture on the Monday with the issues you get when you run many different comparisons using univariate statistics. Because this is going to be the case. I mean, you have thousands of metabolite features, and then you want to run them side by side. There will be many different comparisons. And this will be an issue when you do hypothesis testing and you want to evaluate your p-values that you get out of the method that you use. Because the p-value originally, it says that it's the probability of obtaining the observed results when you assume that there is no true that there are no true differences between groups. And you commonly set this probability to a 5% acceptable threshold. However, if you have, for example, 5,000 features, it's going to affect how we interpret those p-values. Because if you run 5,000 independent tests, and there is a 5% chance of just a chance finding, you will get around, just by average, 250 false positives in your data set. So of course, this is something you have to take care of. And this you can do using different methods to correct for multiple tests. And I guess these are the two most common ones that you can use. It's either the Benjamini-Hochberg method, which basically makes sure that you have a stable level of false discovery rate throughout your data set. So basically, look at the distribution of p-values. But I've decided that we should use instead the Bonferroni method, which is a bit more strict, but on the other hand, is easier to calculate. So basically, it just sets a new p-value threshold by dividing 0.05 with n, which is the number of independent tests you run. So in your case, it's going to be the number of metabolite features you have in your data set. Okay. So in the data sets that you guys have been working with, there are several groups. And what you usually do when you have more than two categories and you want to see whether there's a difference between these conditions, you use ANOVA. And it's a test to test basically the difference, if there is a different means between any of your categories that you have in your data set. It assumes that you have normally distributed data, which may not be the case in your situation because you have quite a few observations. But for the sake of simplicity, we will still use this method now. In reality, you would have to check this assumption before you use a method. What you get as output is basically two things. You get the F value, which is a measure of the ratio between the variance between groups and the variance within groups. And then you get the p-value, which is the level of statistical significance. So just to make sure we're all on the same page, variance is just a measure of how much your observation differ from the mean in your distribution, and it's just the squared of the standard deviation. So you see here on the in the plots, you see an example of high variance, the blue one, and the low variance, the red one. And then you can calculate the F value by looking at the ratio between the between-group variance and the within-group variance. You see two examples of low F value up in the left top corner and a high F value in the top right corner. So you see on when there is a high F value, you have much more larger differences between your groups in the variable you are investigating. All right, and this is something you use in ANOVA because there is a critical F value. When you go over that point, there is a probability of 0.05 that this is just a chance finding. And then, of course, you will have to just adjust this p-value threshold for the number of independent tests. In our case, let's say that we have around 2,500 features, something like that. We may end up with a threshold for a p-value of around 10 to the minus 5. But you will see in your data set where it will end up. It will depend on how many features you have. So in ANOVA, you look at the difference in the means between the groups. What it doesn't say is which of the group actually differs from each other. If you get a significant p-value, it only says that at least two of the groups are different. So that's why we can also perform a Tukey's post hoc tests, which will tell you exactly this. So basically, the pairwise differences between all your categorical variables. So it functions very similar to a t-test. It's just that it takes into account as well that you run comparisons between all your groups. In this case, it's 3 different comparisons because you have 3 different groups. But it's going to increase if you have more different categories in your metadata. All right, with that, I think we can just move on to the notebook. And I guess we have 3 tasks then to look if the metabolite levels in our data sets are different between the different conditions using the ANOVA. I also have a small task where I modeled a way for us to look at the time trends. So to actually visualize how the metabolite levels are increasing with time. And then finally, we used the Tukey post hoc test to look at differences between 2 specific groups. All right. So with that, I think we can move on to the notebook. So we go to our little Word documents and we open this one, right? Yes, and click Open in Colab, just as before. Okay, and you have a notebook called Univariate Stats. You all find it? So if anyone is running into trouble, just tell me, and we can move slowly. All right, so there's just a small introduction to the data set. You already know it quite well by now, so I think it's going to be fine. We can start by just running the install and import R packages part. So basically just, now I forgot what I'm supposed to do. I need to do several things. I need to first save a copy in the drive. So did you all also do that? So you save a copy on your own drive under File and then save a copy in the drive. Sorry? Which files? So it's the same files as before. So everything is going to be more or less exactly the same. The only difference in the beginning is that we will install some packages that are different from before. So if you all have saved a copy to your drive, you can just install the packages. I think it's going to be quite quick. We'll see. A while longer than I thought. Right. So it's done for me at least. So when you guys are done with that, you can just run the next cell to load the packages. Have you all been able to load the packages and to install them? Is someone still stuck? Okay. Right. In the meantime, we can, just like before, we can add our data.
Should be this one, right? The stats.
Is it there?
Yeah.
Oh, yeah, there they are. Yeah, cool. And then just like before, you can copy path and then replace the string with that. Then just import the data. Then you will recognize all the consecutive steps because it's going to be more or less, well, it's going to be actually identical to what you've done before. So I will just basically run these ones. And hopefully you will not run into any issues. We also analyzed all of this before, so hopefully this is going to be exactly the same as in the previous example. So basically run everything down to this cell here, where we check whether the row names are identical to each other. So did you guys manage to do that? Cool. Anyone stuck? Just tell us and we will help you out. So there can be some issues running these methods if we have too many missing values. With missing values, I mean the values we have imputed. So in my case, we have imputed everything that is missing with 1267. And it's going to say in your imputed quants table, the feature table. So if you hover over it, it's going to be like a number towards like the middle. And I just want to see like how many imputed values I have in the data sets. And then possibly exclude some features because they may produce some issues downstream. Just for the sake of the things running smoothly.
So what is it 15? Because I have different data.
Wow. This is going to be 12. I don't know why it's 15. It's from the previous version, I guess. Oops. Good spotted. So you can do that. You can change the 15 to a 12. And then change the number 1267 to whatever you have in your quant table. And then you can run these cells. And then we will visualize how large portion of the data includes many zeros or imputed values, that is. Also calculated like how large proportion of the whole data set is imputed in the cell below. And there are some questions. Yes.
After something that you execute and like it again 2 times false, what would that mean?
Okay. Yes. I guess there could be something that you have different row names, like there could be just some small differences between your metadata and your feature table. And then because of that, they can't match. Maybe someone can help you out with it.
Both are true.
Both are true, then it's fine. It just means that before they were also in order. So it's all right. It's very strange. Yes, I agree.
Can you explain the histogram? Like what would you like to achieve?
Yes. So this just shows like how many percentage, what the proportion of your features or the samples for a specific feature have imputed values. So for example, here there are a few features where there are up to 90% of the values are just imputed. So when we run the statistical analysis, it's going to be some issues because it will be maybe some zero variance between the groups, and then the method might crash. So I decided just to, in the step below, to actually filter out some of these features. This one calculates how many features have less than 50% missing.
So we also have to
Yes. Yes. So every time there's a 1267, you have to replace it with a number that you have it from your own data sets. And replace the 15 with a 12. Yes.
When I do this, I get a histogram with one big block only. So
have you changed the number of the 1267? I can show you here, this one. So this is the number that you can see in your data file. If you hover over your quant table, you see that it says which number has been imputed with. And that number you replace here. So I have 1267. Right, and what I do then is just to filter out here every feature with less than 5%, 50% real values.
Okay.
Yes.
At least like one thing is that you definitely have to change the cutoff that you were using. If you only have one block, you have to change the cutoff. So
but I think it's have you changed like the imputed value in the cells?
I'm just trying. So,
Can I ask now, this, what we do here, double line, important shift value.
Yes.
So this is
Yes.
it means something very important that is only one sample. The next
and of course, those things you could put up on
Are people like so I think we can just like move on through the notebook. There were some questions up there, I think. Someone could. So I have filtered out everything that is missing in more than 50% of the samples. And then I basically just merge the metadata with the feature table using this this cell here. And then we can look at the dimensions of the data set. And this should be relatively familiar to you. Of course, you may have filtered out some of the features. You can see here how many it is if you compare this cell here to what you have in your original feature table. But it's going to be for sure relatively similar to what you had in the beginning. So if you all are with me still, we're going to run the ANOVA. So what we do basically is that we use this function AOV in R. And then basically we pass each feature into the AOV using a for loop. So basically you can just run this whole cell, and it's gonna one by one it's gonna feed in these metabolites into the AOV function, and then it's gonna spit out the results in a long list. So this is what we have here, what we call the ANOVA out. This is gonna be our list of results. And what we want to compare, of course, are the different time points. So every metabolite one by one against the different time points to see if there's a statistical difference between them. So if you run this and try, it's going to be a little slow, not too slow, I think. Yeah. So you can try if that works. Hopefully it's going to be fine. No like a real uproar yet, so I guess it works. So what I think we can do is just to visualize the first entry in this list, and we can do it by this cell below. So we select here by the index 1, like the first entry of the list. And for me, it looks like this. Yes.
So the ANOVA runs from column 5 to all the columns, no?
Yes. So that's yes. So
why does it start from 5?
Yes, because what I did is that I merged the metadata table with the feature table. And so the metadata is first, and then the metabolite data starts from number 5 and it goes to the rest of the table. So did you all manage to get the results from the first entry of the list? Yes, people seem to be quite happy. Sorry? Ah, okay, I see. Maybe it depends on what p-value you have. It could be that because in my case here, the first one is definitely not significant. So there is basically no difference. Maybe you have like an asterisk or something. Yeah, pretty cool. So, I mean, in theory, we have all the results here in this list, but it's very inconvenient to work with it. So I just want to extract the information that we want out of this. So basically, I think it could be good to generate just a table where we have the feature ID as one column, then the p-value from the ANOVA, and then that we perform this Bonferroni correction of the p-values in one separate column, and then the f-value, which is the ratio of the variances within group versus between group. And you can do this just by running this. I don't think we have time to go through like exactly what happens here because we don't really have time for it. But I think we can just run it and hope that it's going to work. At least here it did. So how did it go for you guys? You nod. Good. People are happy. Sorry? So it creates like a data frame with your results. So what we do and this of course, this is a long list or quite big table because it's one row for each metabolite. So I want to do is just to display the most significant findings. And we can do it in this cell below, where we basically say that we take our result file and we arrange it after p-value, and then we select the top 20 entries in the list. You can select like any other number that you find interesting, but I selected 20 because it's easy to visualize. And then it looks something like this. So you have your metabolite ID. So I guess it's the ID from MZMine, and then it's the mass and the retention time, I would assume. The p-value, and then the p-value after multiple test correction. We also have a column which says whether this is a significant finding or not. And then the f-value, which is like ridiculously high for these ones. So it means that there's an extreme difference. So probably in one of the group, all the metabolites were below level of detection, and in the other group, they were relatively high. So that's why we get this like very impressive f-value. We can also plot this, and we use the ggplot package to do this. Basically, what I want to do is to plot the f-value on the x-axis, and as you see here, and then I log it just to make sure that we can easily visualize it. And then on the y-axis, we will show the minus log of the p-value to see like the most to display the p-values basically. And then we color it after significance, whether it's significant or non-significant. So try to run it. For me, it looks like this. I also added a little text here, which will enter the names of the metabolites, the 5 top metabolites. If there may be some of them that's maybe interesting for you, you can show them. There are too many findings in order to display all of them, of course, but it could be nice to show a few just for fun. Did you all manage to do this? Cool. So it tells us that the higher the F value is, the larger is the difference between the groups, at least two of the groups. And then it tells us like how significant that finding is. And it seems here that, at least in this case, data set, it seems to be like a quite large portion of the of our data set that is actually significantly different between these two, between at least two groups. Right? You all with me? Cool. If you want, you can also export this as a PDF. And if you run this, it's gonna show up in your sample data, I think. Should be here, right?
Click again on the folder.
On this one?
No, the one on the left.
On this one?
Okay.
Ah, there it is. Cool. And we can actually open it to see as well if you want. If you want to look more closely, maybe zoom in or something. I don't know.
Remember to download.
Yes. You can download it as well, yeah. Just by clicking here and then download. Maybe we also want the results as a CSV file, just a list of all the whole table. Then you can just run this one, write CSV, and then it's also gonna pop up here in the. Oh, here it is. Pop up here, and you can open it. I guess we're running quite late, so we should try to move on. I have this middle section where I plot how the average metabolite differs over time. It's quite long, and I think maybe it's better that we actually have time to also do the Tukey tests, so we can see differences, but I can just show you what I got from this part. So I'll just run all the steps. It's just basically arranging the data for what I want to plot. So it shows something like this. So this is just like the average metabolite level at each time point. So I have just subtracted the time point 0 and then just see how they change over time. And this, of course, is a very like coarse measurement of how this the metabolites differ over time, but we can still see that it seems like there is a biggest difference between time point 45 and 0, at least in my case, which is of course expected. So because of that, I thought it was a good idea to run the Tukey postdoc test and then extract all the differences, the like group-wise differences between time point 45 and 0. And then also export this as a plot and as a text file. Are you all still with me? Yes, cool. So we can just run again another for loop. So it basically takes the lists that we get from the ANOVA and then extracts all the information it needs and then calculates the group-wise differences between all the different groups. If we just run it, you can try as well. It's going to be done pretty soon, I think. It's lower than the ANOVA. Right. And then again, I just wanted to display like how the results look. So if we just again select the first entry of our list of results that we have spit out here, which we call Tukey out, it looks something like this. So what we get is the differences between the different groups. So in this case, we are interested in 45 minus 0. So this is just a difference in levels. And then these are the p-values. So these are the information I want to extract from this. So this is what happens in the cell below. So again, we extract the information that we're interested in. So in this case, it's the difference in average between levels, between the time from 0 and 45, the p-value, and then we do a Bonferroni correction for the p-value in a separate column. And then finally, we calculate whether it's a significant finding or not. So if we run this whole cell, it's gonna give us this result. We can again look at can arrange our result file after the p-value and look at the top, in this case 20 findings, and we get something like this. So we have the difference. It's measured in standard deviation units, that's why it looks almost like the same for all of them. And so it's no matter of like if it's a high or low area. We get the p-value. Something a little bit strange happens here. Can you spot it if you look here in my plot file? So basically, it's this method in R doesn't calculate any p-value that's lower than 2.2 to the power of -16. And after the internal correction for 1, 2, 3, 4, 5, 6 different tests that you do in the Tukey test, it will correct this to this value. So that's why this is like the minimum p-value that's going to display. So which is a bit inconvenient, but this is how it is for this method. I didn't realize it until just quite recently. So it's going to show also, of course, then when you do the Bonferroni correction, because it's all going to based on this p-value when you calculate it. So it's like the top findings will all look quite similar. We can plot this using a volcano plot. So on the x-axis, we will show the difference between the groups, and then on the y-axis, the p-value. We can just run this cell. We will also enter the names of the most significant findings. And it's going to look a little bit weird like this, but it definitely shows that a lot of metabolites are different between the different conditions. Do you get something similar? Okay, so you see here that there's like a p-value ceiling here. It doesn't really go any lower, which is a bit inconvenient, but yeah, it's how it is in this case. Anyways, we can also export this again to a PDF and to a CSV file. I just wanted to end by making some kind of sanity check. So I just took like the top finding in my list and just wanted to plot it to make sure that what we see is that we haven't done anything strange. So I just plot it in another ggplot using box plots, and then it's going to look something like this. So if you want to run this, you have to go to your results list, and then take this whole, like any metabolite that you're interested in, and then copy it and replace this value here with it. And then you can look at that specific metabolite, how it differs between these different time points. And here we can see that there is a very big difference between time point 0 and 45, which is exactly what we showed in the Tukey tests. So it's kind of a sanity check just to make sure that we didn't do anything strange because we got so impressive findings. So now we know that. Did you guys get anything very different, or does it look more or less similar to my results? Yeah, you nod, kind of, yeah. Well, that's actually everything I had. If you would want, you can also export any of these files, anything like that. And Yeah, cool.